Hello and welcome back to our algebra. Before we get going on a new topic in algebra, quick review here. But before we begin our review, I have a question for you, which is when do old clocks die? When do old clocks die? So before we do, the ancient Greeks didn't really have algebra, right? They would have thought about this 12 times 27 as an area problem. What's the area of a rectangle that's 12 by 27? So, and again, we've done this before when we've done multiplying, so I can think about this as right? This side is 10 and 2, that makes 12. And this side of my rectangle is 20 and 7, that side is 27, right? So if I look at the area, this rectangle is 200, this rectangle is 70, this one is 40, and this one would be 14, right? And then I just add all those together. So this one is 270, this one is 54, and I add those together and I get 324. That's what I'll get. Well, this is the way the Greeks would go ahead and look at this problem. Now, I know most of us don't multiply this, but we did talk about this back when we did surds. So let's look at this one. Again, we can think about this as an area problem. All right, one side is 2 plus root 3, and the other side is 3. Now, it really wouldn't make sense to have a minus there. But the beauty of this model is it works anyway. So imagine the length of that side is 3, and that's minus root 3. So again, we can do the same thing, right? 3 times 2 is 6. 2 times minus root 3 is minus 2 root 3. That's going to be 3 times root 3. And root 3 times minus root 3 would be minus 3. Okay? And if I combine these things together, I see I have a 6 and a minus 3. All right, I have numbers. I have a 6 and a minus 3, which gives me 3. And I have 3 root 3 minus 2 root 3, which would be 1 root 3. So this simplifies to this. So again, this is another way, we did this in Module 1, looking at the area model to go ahead and multiply. Okay, so again, we've done this, right? This is what we were doing the first part of Module 5. Again, we know how to do this, but I just want to look at the area model because it's going to be very useful in something else that we're doing coming up. So again, right, the area model, imagine this is a rectangle. One side is x plus 3. That's how long one side is, and the other side is x, and 2 is the other side of the rectangle. So to multiply these, x times x is x squared, x times 2 is 2x, x times 3 is 3x, and 2 times 3 is 6. Again, I can combine all my like terms. I'm going to end up with x squared. 2x plus 3x is 5x. And 3 times 2 is 6. So again, most of us by now, we're really good at multiplying binomials, expanding brackets like this. We might not need to do the area model, but this is going to come in really useful when we start talking about a topic called completing the square. What about going the other way? What would the Greeks do? They didn't have any algebra. They like to think about things geometrically. So I ask you to factor 11. Again, they would look at it, the Greeks would say, all right, so I have a rectangle area 11. What could the sides be? Well, if we're just talking whole numbers here, the sides, there's no choices there. It's 1 and 11. 1 times 11 is 11. Okay, what about if I wanted to factor 18? Well, I have some choices, couldn't I? I could do 1 times 18, right? I could do 2 times 9. I could do, again, if we're just talking about whole numbers, 3 times 6. Those are different ways that I could factor 18. 1 times 18, 2 times 9, 3 times 6. So it's really doing the reverse of what we just did. Okay, so we've been doing a lot of factorizing these. How can we use the area model? Well, again, it's the same thing. It's thinking, what could it be? What could the sides be, right? And again, this isn't really the way we go about doing this, but it will come in handy here in just a second. So I know I'm going to need an x and an x, right? And if we think about what happens here, right? What happens in this rectangle down here, right? Well, I have two whole numbers that multiply together, right? And they need to multiply together to give me 12. Okay, what happens in this square and this square? Well, we know those are going to add together to give me that 7x. So I need things that add to 7, don't I? So I'm looking for things that multiply to 12 and add to 7, which must be 3 and 4. So now the order doesn't matter, does it? 3 and 4, because that 3 and 4 are going to give me a 12, and that's going to be a 4x and a 3x and an x squared, and that's going to give me what I'm looking for. So again, we've been doing this. This isn't how we would actually go about factorizing these, but I just want us to think about these because we're going to use this very shortly.